Hello, today we will discuss the second part of the module that we have already discussed in the first video. So we are going to the proof of that section. So in the first video we have discussed Wien's radiation law and Rayleigh-Jeans radiation law. Now let us move ahead to the proofs of these two radiation law by Planck's radiation law in blackbody radiation. Okay, so Wien's radiation law and Rayleigh-Jeans radiation law, these are two different laws, whereas Wien's radiation law is applicable for shorter wavelength and high temperature, shorter wavelength and low temperature. Okay, and Rayleigh-Jeans radiation law is applicable for bigger wavelength or larger wavelength and high temperature. These two are the condition of the specific radiations law provided here. So let us move ahead to the Planck's radiation law. We have discussed these things earlier. Okay, so let us move ahead to the Planck's law in blackbody radiation, BBR. Okay, so the formula was U lambda equal 8 pi Ch by lambda to the power 5 1 by e to the power Ch by lambda kt minus 1. We have already told all the terms of this equation in the first video. Let us move ahead to the proof of these two radiations law by this one. So let us consider this is to be question 1, and for the proof of the first one is Wien's radiation law. We have to assume the wavelength to be shorter and the temperature to be the lower one. Okay, so to start the proof, at shorter wavelength we will write this at shorter wavelength and low temperature, at shorter wavelength and low temperature, equation 1 becomes before that let us consider Ch by lambda kt to be what? X. So therefore e to the power x is nearly equal to what? E to the power x plus 1, neglecting where lambda is very less than 1 because shorter wavelength, therefore x is very greater than 1 because these two are inversely related to each other. So this can be written. Okay, and just substituting this at equation 1, we will have U lambda equal 8 pi Ch by lambda to the power 5 into 1 by e to the power Ch by lambda kt is x plus 1 minus 1. Okay, so just cancel out these two. We will left with this term. So U lambda equal to what? 8 pi Ch by lambda to the power 5 1 by e to the power x was how much? Ch by lambda kt. Okay, this is the relation that we are getting from that point. Now just by using one more thing, we know that E lambda equal to C by 4 U lambda. That is the concerned part, and this is to be known, this formula is to be known to everyone to do this derivation. So using this we can write U lambda equal to what? 4 E lambda by C. So just substituting that 4 E lambda by C equal to what? 8 pi Ch by lambda to the power 5 into 1 by e to the power Ch by lambda kt. Okay, now E lambda equal to how much? We just multiply this 4, this will be cancelled out for 2 times, and E lambda equal to what? 2 pi c square h by lambda to the power 5 1 by e to the power ch by lambda kt. Okay, this is the term we are getting. Actually, if you see carefully, 2 pi c square h, this the whole term is a constant part. So we can write E lambda equal to C1 by lambda to the power what? 5 into e to the power C2. Okay, just like that. Just we have to do like that to continue with this question. So we will left with this relation. So this is the condition for Wien's radiation law. C1 by lambda to the power 5 1 by e to the power C2. If we write d lambda both sides, so this is the condition. So till now we are left with this. Actually C2 was considered to be ch by lambda kt, but check it carefully. Is there all the terms constant? C1 was what? C1 was 2 pi c square h that we have derived, but C2 was not all the terms constant was there. Ch is a constant, c is what? C is the speed of light in vacuum, h is what? Planck's constant, itself a constant, k is the Boltzmann constant, but lambda and t are not the constant things. So C2 cannot be written as the whole to be constant. So C2 is only ch by k, not the lambda t. So we have to write there E lambda to be C1 by lambda to the power 5 1 by e to the power c. We are left with lambda t 1 by lambda t into e to the power c2. What was c2? C2 was where only ch by k, this thing is only the constant part, and lambda and t are not the constant things. So the last result can be written as E lambda equals C1 by lambda to the power 5 1 by e to the power C2 by lambda t. Okay, that is the relation for Wien's radiation law. We have derived the Wien's radiation law from Planck's law of black body radiation. So now we will derive the second one, which is Rayleigh-Jeans radiation law. So we have already derived the Wien's radiation law. So let us go for Rayleigh-Jeans radiation law. Rayleigh-Jeans radiation law. Okay. So now we know what is Rayleigh-Jeans radiation law. Rayleigh-Jeans radiation law is 8 pi kt by lambda to the power 4 d lambda. This is the formula, but we have to derive this one from what? From the Planck's law in black body radiation. What was Planck's law in black body radiation? Planck's law in black body radiation was 8 pi ch by lambda to the power 5 1 by e to the power ch by lambda kt minus 1. This is the Planck's law in black body radiation. So let us consider to be equation 1, and we have to do such things to convert this into this one. This is the Rayleigh-Jeans radiation law. So to convert this, we have one option. We have to consider this ch by lambda kt to be something. Okay, so according to me, let us consider it ch, for my sake of easiness, ch by lambda kt to be alpha. We have let this to be alpha. Now what we can do, e to the power ch by lambda kt can be written as e to the power alpha. Okay, very good. So after that, what we can do, we know Rayleigh-Jeans radiation law is valid only for larger wavelength and high temperature. So for larger wavelength, for यहाँ पे लिखेंगे हम लोग, for larger wavelength and high temperature, what we can write For larger wavelength, lambda should be much greater than 1, so that alpha should be what? Much less than 1, such that we can write e to the power alpha nearly equal to what? 1 plus alpha. If alpha is very large, not the large, if lambda is very large and alpha is very small, when alpha is very small, we can write this. Since alpha is very small, we can write this. So after knowing the value of e to the power alpha to be 1 plus alpha, we can substitute this here. So the equation 1 becomes, we are coming this side, equation 1 becomes what? U lambda d lambda. U lambda is, you are guys already know that U lambda is the energy density, equal to 8 pi ch by lambda to the power 5, 1 by e to the power ch by lambda kt, means e to the power alpha. Okay, so this is e to the power alpha. So e to the power alpha is changed into 1 plus alpha. Let us keep it e to the power alpha once. Now in the next step we will change this. We will change this to 8 pi ch by lambda to the power 5, 1 by e to the power alpha by 1 plus alpha, replacing e to the power alpha by 1 plus alpha, and the 1 will be cancelled out. We will be left with alpha. Alpha is nothing but ch by lambda kt. So now substitute the value of alpha here. We will get u lambda d lambda. Do not forget this d lambda with it. Okay, keeping that d lambda together, we can write 8 pi ch by lambda to the power 5, 1 by alpha. What is alpha? Alpha is this, ch by lambda kt. So lambda kt will go to the upper side into d lambda. So now let us think, what are the terms that can be cancelled out? So ch can be cancelled out easily. Okay, lambda to the power 5 and lambda, there one term of lambda can be cancelled out, and this term means in the denominator we will left with lambda to the power 4. So u lambda d lambda can be further written as 8 pi kt by lambda to the power 4 d lambda, isn't it? So we have proved the Rayleigh-Jeans radiation law by using Planck's law in black body radiation. That was the u lambda d lambda equal to 8 pi kt by lambda to the power 4 d lambda, and this is the same as that thing. We have proved this one by using equation 1. So this is how we can prove this equation, and for each derivation you will be getting in your examination around 2 to 3 marks for each derivation. These derivations are so easy if you practice it very well.